Okay, so okay, so sorry, today actually there's a big snow, so let me just try to present the lecture online. Okay, so let me share my screen here. Okay, so uh okay, so yeah, so okay, so let's continue the presentation and then let's see. Okay, so here we are on this holomorphic covering space, and then let's see. Okay, so it's okay. So U is a unit covered set, and then yeah. So we have constructed U double prime phi U prime is a local holomorphic chart. Uh oh yeah, yeah sorry. So this is by definition. Yeah. So we we yeah we pick the collection. We pick the script A to be the collection of this local complex chart of this form, right? And then where this U and this U prime, and then the restriction, they have the property that this this is a local holomorphic chart in this X tilde, where this U double prime is a connect component of the gamma inverse of U. Okay, okay, so here, yeah, we want to show that this A is a holomorphic atlas in X. So basically, we have shown that um, the transition maps is holomorphic. Okay, so therefore, this A is a holomorphic atlas. Okay, so okay, okay, so now we want to verify this. Okay, so we want to show that the map vertical gamma from x tilde to x is holomorphic with respect to this holomorphic structure. Um, okay, so since given a local holomorphic chart in A, uh, oh, okay, so we have that phi composed with vertical gamma restricted on um, U double prime inverse composed gamma is equal to phi on this U double prime. Okay, so uh, let me see if I can do a whiteboard here. So um, uh, wait. Yeah, sorry. Let me open my whiteboard. Uh, okay. All right. So here, let's see. Let me see if I can just paste everything here. Oh, oops. Okay, it can be pasted here, but um, yeah. So it has some. Uh, so let me see if I can take the just taking the um screenshot. Okay, here we go. Okay, all right. So here, um, okay, okay. So here, let's draw a diagram. Okay, so this um okay, okay, so what is this phi? Okay, so remember that this phi is simply just, okay, so I can't turn my share now. So yeah, okay, so remember that this phi is, um, Okay, so from here we know that uh okay, so for the information about this phi, um wait, why can't I why can't paste it? Uh okay. Okay, good. Okay, so this is about the phi. Okay, yeah. So so this phi is basically it start with the u double prime, a kinetic component of uh wait, can move this. Okay, maybe I can move it to here. Okay. Okay. Yeah. So this phi basically it start from a kinetic component u double prime of this gamma inverse u. Okay. And then it maps to like an open set uh u prime, right? So and then this u is an evenly covered open subset of X. Okay, so yeah, so basically we start with X and then U and then we pick it upstairs U double prime. And then okay, so this phi maps U double prime to U prime. So U prime is like C, right? Uh yeah. And then uh yeah, so okay. So okay, so this is the map phi. Okay. Okay, so now, okay, so it's equal to phi on double prime. Uh, okay, so we first we start with uh vertical gamma. Okay, so this is just the right. So if it okay, so on this U double prime, right? So this is just you project it down, right? You map it onto U, and then you do the inverse, then you get it back, and then you map it phi. Yeah, so that's exactly equal to that. Okay, so so since then, so given a holo yes, so we do have this property. Okay, um, so why can't I just use another uh? Okay, never mind. Okay. Yeah, so we have this property. Okay. So so what do you want to show? So uh if a prime is a holomorphic and let's say okay, so okay, so why does this shows that this gamma is holomorphic? Okay. Ah, okay, so why this is holomorphic? So let me okay, so we want to show that this gamma is holomorphic with respect to this holomorphic structure, right? Where for the for the for the for the vertical gamma, basically what you do is that uh oh okay. So uh so if you take any chart, okay, if you take any local chart, uh and then uh and then you have the U on okay, so yeah, I think yeah, I'll just leave it out to for you to verify this one. Okay, yeah, so yeah, so basically, I think the idea is that you take any local chart and then you show the Actually, the function is a holomorphic function uh, on this. Oh yeah. So you show that like this. So you show that yeah. So you show the convolution is a holomorphic function that's being defined on the u double prime. Okay, so using the definition. Okay. Um. Okay. Uh. So finally, let's see. Okay. So maybe I'll just yeah. Maybe I just do that. Okay. So um. Okay. Okay. Maybe I just okay. Okay. Uh. Okay. So now, so finally, if A prime is a holomorphic atlas on X, with respect to which the covering map gamma is holomorphic, and we have another chart in this A prime. Okay, and we pick a chart in this A, and then the coordinate transformation on the intersection is given by um uh u intersect. Okay, so the coordinate transformation on this u intersect q, okay, is given by um so wait. Okay. Okay, I think this sentence is not finished yet. Okay. Yeah. So let me paste it. Um okay. And is therefore holomorphic as a composition of holomorphic maps. Okay, so okay, this one. Okay, so here I have that um this one I want to show that this map is a composition of holomorphic maps, right? So so here what I have is that um so I have the phi composed with uh gamma retreat on this u double prime inverse and inverse. Uh okay, okay. Yeah, so I think I showed last time that this is just simply just this whole thing is just gamma composed with phi inverse. Okay. And then yeah, so when we compose this wedge to this whole thing, yeah, so this is equal to the wedge composed with vertical gamma composed with phi inverse when we restrict on the intersection. Okay. And then so why these are all holomorphic maps? Um I think we use the same trick as we used last time, right? Because we can regard the phi as yeah. So we give a homomorphic structure basically of the open of this open set in C. Okay. Uh, by just itself, and then this we just show that we show that this gamma is we just show that this gamma is holomorphic. Wait. Uh. Oh, okay, yeah. So this A prime, okay. So this A prime is a holomorphic atlas with respect to the current map is holomorphic. Okay, so Uh, wait, hold on one second. Um, so yeah, so this gamma basically is holomorphic on both holomorphic structure, right? Uh, is holomorphic. Okay, so and is therefore holomorphic as right that inverse map is also holomorphic. Uh, so okay, so why this phi inverse is holomorphic? Um, with respect to this um, holomorphic as a composition of holomorphic maps. Okay, so I'm not sure why this. So I know that when you look at the when you look at the when you look at the when you look at this holomorphic chart, right? When you look at this A prime, yeah. So when you look at the holomorphic atlas A prime, mm, yeah, we know that this gamma is definitely holomorphic. Oh, sorry, not gamma, but this wedge is definitely by itself holomorphic when you yeah, uh and then this vertical gamma is also holomorphic, but it's holomorphic as a composition. Wait, wait, hold on one second. So okay, so yeah, okay, so here, okay, so here there's nothing to do with the holomorphic structure. So this is just the uh map from wait uh yeah, I want to say that it is a map from uh okay, so yeah, so this gamma okay, I take my words back. Okay, so yeah, I think it has something to do with the holomorphic structure, but so here this map by itself is a map from I think uh from a subset. So okay, so basically you take the inverse of this U intersect Q, right? And then you focus on the inverse image of this set under the gamma retreated on this U double prime inverse, right? Um, and then you get some set upstairs, and then and then you map it to the phi, right? And then it becomes a set in this U prime, right? So here you should start with this U prime, right? So and then you yeah goes to you goes to gamma and then you apply gamma and then you apply a wedge. Yes, you apply a wedge and then it becomes another like set in C. Okay. So so here basically I think what is going on here is that um so here yeah you also do the same thing, right? So you give this say a holomorphic structure and then yeah uh yeah so why is it holomorphic? Okay, so uh Yeah, so I know that it has holomorphic structure. Okay, so maybe I want to leave it as an exercise. Okay. Um, so an exercise is to show that um why this map wedge composed with gamma composed with this phi inverse is holomorphic as a composition of holomorphic maps. Okay. Okay, holomorphic maps. Okay, yeah. So yeah, I'll leave it. I'll leave out an exercise. Okay. So so then let me just wipe out a little. Okay, so then the inverse function theorem then implies that its inverse map is also holomorphic. Yes, because uh, it is clearly a injective map, a bijection. Okay, a bijection. Okay, and then thus these A and A prime determine the same holomorphic structure on X. Uh, Inverse map is also holomorphic. Thus, these A and A prime determine the same holomorphic structure. Um, okay, so okay, so they are yeah, so the transition maps are holomorphic, right? Okay. Yeah, so uh the inverse function theorem implies that the inverse map is also holomorphic. Uh, so yeah, so this shows that they are holomorphic. Yes, they are like holomorphically compatible. Okay, and okay, so therefore we have uniqueness. Okay, um, okay, so now, uh, okay, so let us prove the other part, the part B of this theorem. Okay, so okay, so what is part B? Okay, I think I can. Uh, am I am I I want to move. Oh, how do I really? Okay, I can move here. Okay. So here let's prove part B of this theorem. Okay, so let me state the part B of this theorem first. Uh, okay. Yeah. Maybe let me show you the prompt first. Uh, okay. So here is the first part of the prompt, and then let me show you the second part of the prompt. Um, okay. Okay. Sorry. Okay. Maybe I can wait. Shoot, I don't think I can change it. Okay. All right. So this is a prompt. Okay. So okay. So for part B, okay. So we basically have that if the gamma hat is a subgroup of this group gamma, we have a commutative diagram of holomorphic map. Moreover, if I pick any x naught in So if I pick any base point in this x naught tilde in this x tilde, and we pick and then we let x naught to be the uh, projection onto the x by the covering map, and then um, and then we have uh, x naught hat. Oh, sorry, I think this is just the quotient space mapping. Okay. And yeah, by the quotient map. Okay. So and then we also have the x naught hat to be the okay. So to be the outer quotient map. Okay. Under this group with respect to this subgroup. Okay. So this is x naught hat. Okay. And uh and then okay. So and then we have that. Okay. These Okay, so this chi from the deck transformation group of vertical gamma to pi 1 x naught and wait, um, from, yeah, okay. Okay. So this chi from the deck transformation group of this vertical gamma to the pi 1 x naught. Okay, and we have and this chi hat from the deck transformation group of respect to this covering map uh, to pi 1 of x hat, x naught hat to this space are the corresponding group isomorphisms. Okay, and then we have this the composition, right? So the composition from pi 1 of x hat, x naught to pi 1 x naught. Uh, yeah. So it's equal to the gamma hat push forward. Okay, so it's equal to the is gamma hat push forward. Uh, okay. Okay. In other words, the action. Okay, I think this gamma hat is just the gamma hat that we defined before. Okay, and then in other words, the action uh small gamma hat of in this pi 1 x hat x naught hat is x tilde is the same as that of yeah. So gamma hat push forward of this small gamma hat, which is equal to uh the vertical gamma hat of small gamma hat. Okay, so mm, okay, yeah. So this is by definition of the push forward. Um, yes, and then this part one, yeah, which is in okay. The action of yeah, I think yeah, okay. So this is the action of gamma hat on this uh pi one x hat x naught hat. The action of gamma. Okay, so what is small gamma? So small gamma is a okay, small gamma is a group. Um, Okay, I think there's a way that for you to define the action. Okay, I think the way you define the action of part one is uh yeah, so it's by the uh yeah, it somehow you fix a starting point and then you do a lift of this map, right? And then you say that the image of that action will be the endpoint of this lift of the unique lift. Okay. With that um fixed starting point. Okay. Um, it's the same as that of. Oh, okay. It's the same action of. Yeah, it's the same action of the gamma push forward of this uh pi one. Yeah, sorry, this gamma hat push forward. Yeah, so here you have a loop. Let's say here, sorry, it's a equivalence class actually, but yeah, so you have a loop here, and then you push it forward to okay, you push it forward to um a loop in this part one x naught, and then you talk about the action of this loop of spares. Okay, I think this is what he means here. Okay. Um, action gamma. Okay. 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 All right. So yeah. So that's okay. Let me present the proof here. So um. Okay. So okay. So okay. So here for the proof are part B. Um. Uh. Suppose. Wait. So okay. Uh. I think the thing that we want to, I think the thing that's, yeah, so I think that the idea is that we do have a topological argument about this commutative diagram, right? So here, I think the only difference is that here we require the map to be the holomorphic covering maps, right? So we require it to be the holomorphic covering maps. And I think the second add-on condition is the same as we proved a while ago, right? I think it's just purely topological argument. Uh, okay, okay, okay. So let's see. So, yeah. So for the proof of part B, suppose this is a subgroup, and then theorem 10.4.6 gives the required commutative diagram of topological covering maps, and then part A gives the holomorphic structure on X hat. Okay. Part A gives the holomorphic structure on X hat. Uh. Oh. Okay. Yeah. 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 So. Okay. So I think what's going on here is that for part A, um. So yeah. So I think this group is yeah. So let me paste it here. Yeah, so I think the idea is so for part A, right? So uh let's see. So here this is our assumption, right? So this is a simply connected Riemann surface, and then this gamma is a subgroup of the automorphism group that is X the continuously fitted on X. Okay, so here we take a so here we just take a subgroup of this group, right? So subgroup also yeah, also X coverly continuously and wait freely. Yeah, why it I think it also acts freely on this X tutor. Okay, so if you have a subgroup, okay, and and then yeah. So what does it mean for it to be free? Okay, okay. So maybe you can check the subgroup is acting on freely. Okay, so and then okay, and then uh freely. Okay, and then okay, so we have the same setup here, and then yeah, so the proof of part A actually gives you the holomorphic structure. It gives you the holomorphic structure on this on this X hat, such that the covering map is a holomorphic covering the quotient map is actually a holomorphic covering maps, and then uh um and then yeah, okay, so yeah, so and then okay, and then part A gives the holomorphic structure on this, okay, which with respect to this is a holomorphic. Okay, so it follows that the covering map is also holomorphic. Okay, so I think what we left is just to check this gamma hat is also holomorphic because uh okay, because locally the map may be written as the composition of the holomorphic map. Uh oh, okay, gamma with a local holomorphic inverse. Yes, I think this is a uh wait. Uh yeah, so here basically what you do is that so if you take yeah, so if you take any set wait, what is gamma again? Um yeah, so you okay, you quotient by the equivalence. Okay, so this set they are the equivalence relation of this X by this group gamma hat, and then okay, you map it to the same X but with the quotient relation by the gamma. So why okay, so why okay, there is a um written as a combination of holomorphic map. Okay, so this is gamma hat. Locally, the map may be written as the composition. Okay. Okay, so with a holomorphic inverse. Uh, okay, so basically for each point, so for each point on this X hat, right? I think we can find a evenly covered, yeah, we can find a evenly covered neighborhood. Um, wait, but why? Uh, so here we have X in X gamma hat, right? So, so this is just the quotient math, and then with okay, okay, okay. So somehow, okay, so somehow we map it to X. Okay, so somehow we map this equivalence relation back to X. Okay, by the evenly coveredness. Okay, and then we can also do the projection. Okay, yeah. So this, yeah, locally we can do that. Okay. So and then the composition of the holomorphic map. Yes. Okay. Yes, with a local inverse. Okay. So so okay, so oh okay, because these are all holomorphic maps, right? Yes. Okay, then this is holomorphic. Okay. All right. So okay, so yeah, okay. All right, so this is proved. Okay, so uh let me see. Okay. Okay, so okay, sorry. Let me just state uh state the corollary and let's see whether we can just finish or not. Okay, so here okay, so this is the next corollary. Okay, so let X be a Riemann surface and let this X naught in this X. Okay, so we pick a base point of this X. Okay, and then let gamma be the subgroup of the pi one X X naught. Okay, so subgroup of the pi one. Okay, and then up to holomorphic equivalence of holomorphic covering spaces. There are a unique covering Riemann surface. Uh, gamma hat to X. Sorry, gamma hat from X hat to X. Okay. Uh, and a point X naught hat uh in gamma hat inverse of X naught. Okay. Such that the homomorphism gamma hat push forward from pi one X hat X naught to pi one X X naught maps. Okay, isomorphically onto gamma. Okay. In fact, if okay, so if this gamma vertical gamma is the universal covering space, then we have the commutative diagram. Uh, okay. Here we identify uh hmm, wait. We identify pi one x. Okay, we identify pi one x. Okay, we identify pi one x x naught that contains the uh group gamma subgroup gamma. Yeah, with the deck transformation group of uh respect to this gamma. Okay, okay. Uh, covering space. There is a unique covering Riemann surface. Okay, so if oh okay. Okay. Yeah. I think this has two parts. So yeah, so the first part is uh the up to yeah to show that there is a unique covering Riemann surface uh at a point in the fiber such that the homomorphism maps pi one x x naught isomorphically onto the group gamma, and then the other one is if we have a universal covering space, then we have the commutative diagram. Okay, okay, so let's see the proof. Okay, so okay, so for the proof. Okay, so this follows immediately from theorem 10.3.3 and theorem 5.1.1. 1.2, which gives the existence of the holomorphic universal cover. Okay, so let's see what is theorem 10.3.3. Okay, okay, so which gives the existence of holomorphic universal cover. Oh, okay. So yeah, so for the theorem 10.3.3, the idea is that so here this X is a Riemann surface, so therefore it is connected, and also it is locally similarly connected. So therefore, uh, by the theorem 10.3.3, there exists a universal covering space. Okay, there exists a universal covering space. And then by the theorem 5.1.2, we so 5.1 wait, why yeah, so 5.1.2 uh x yeah, so we have that uh there is a yeah, so actually so yeah, so there is a universal holomorphic structure on this X hat, respect to which the covering map is a holomorphic covering space. Yeah, so that tells you that whenever you have a topological covering space, and then this the the image of the image of the space is actually a complex manifold, then there is a unique holomorphic structure. Yeah, so this is the theorem 10.5.2. Yeah, so here we have the yeah, we have the property that if we have the vertical gamma as a topological covering map, and then there is a unique holomorphic structure on this covering space. Okay. And then theorem, yeah, so that gives you a existence of the holomorphic universal cover, and then the theorem 5.1.7, the construction of a holomorphic covering from a okay from a properly discontinuously free group action by automorphisms. Um, okay, so then uh, so we have the okay, so now we have our construction of the holomorphic universal covering space of this X tilde uh, uh, okay, okay, so then we have the commutative diagram. Okay, so here we have okay, so this is the suppose that this is a universal covering space and with the uh, holomorphic structure. Uh, okay, subgroup. Okay, I there is a unique covering Riemann surface. Gamma at a point. Okay, okay, okay. I think this is by the result that we just proved. Okay, so because yeah, so namely uh yeah, so namely here if we take any gamma as a so the group gamma hat is as a subgroup of this gamma. So yeah, so therefore we get a commutative diagram, right? And then yeah, so we require this x tilde to be a simply canonical Riemann surface, okay? And then this gamma is a yeah so it's a subgroup of the automorphism group of uh oh okay okay so automorphism group that acts properly discontinuously and freely on this x tilde. Okay, so here we do have that this gamma is a uh yeah, so we identify the group gamma with the deck transformation group, right? With respect to the home with respect to this gamma, and then uh since this gamma is a holomorphic map, so yeah, I think we show that this is actually a automorphism, um, but I don't quite sure. Uh, okay, um, so why is it auto? So what they show that is a auto. Okay, so I think I'll leave out as an exercise for yeah for me, and then okay, so yeah, so because the time yeah, I think I'll just stop at this point. Okay, so uh and then uh uh yeah, and then I'll continue next time. Okay, thank you.